Sterling Allen here. I just got back from my trip to see Brillouins over in near Oakland, California, and I'm going to be showing 3 videos from that trip with Brillouins, and this is the first of 3. The first one is we're going to show their Berkeley facility, which is where their headquarters are, and they've got their wet system and the HHT system there. We saw both of those running and in process of taking measurements and whatnot. And then the second video, we're going to show SRI International, their HHT system, which is the hot system, which gets up to 600 degrees Celsius. They have an HHT system there. It's a little more, there's more sophisticated equipment measuring that, but pretty much the same setup, but a little different in terms of the equipment that's measuring it and where the wires are running and whatnot. And then the third video will be kind of a round table discussion where we're talking at SRI with Mike McCubry and some others there. Actually, there's 4 videos. I've already posted the first video, which was an interview I did with Mike McCubry after everything was done. So this is really the second video, second of 4. And by the time we're done, there might be 5, but we'll call this video 2 of 4 for now. And we're going to show you the facilities there in Berkeley.
This is sort of stages going through the new wet boiler system. This is the pressure vessel blank. Then there's a lot of machining that gets done on that. And then we've got these caps that slip into the end. We have a plexiglass version, so this fits up in here. And we have a piece that goes around it. There's caps top and bottom. So this allows us to assemble a complete system and operate it, and we'll be able to see visually when the system goes active. When you actually have a reaction happening, you wind up with a cloud forming around the cathode. When it's just electrolysis going on, you have bubbles nucleate and they float up. When you actually have a reaction going, you get a cloud emanating from the cathode in all directions.
So it actually luminesces.
No, if you actually get luminescence out of it, it's damaging the core. Okay. Mike McCubry and Fran Tanzella and my team here had a conversation actually about that exact thing. There's a video on our website showing showing some fire coming out of the core, and we think that the light that comes off of that out of that you see in that video is actually metal ions being blown off the surface of the core. As soon as you get luminescence coming off of the core, sustained luminescence like what you see in the video, phase 1 video on our website, it damages the core and it eats it very quickly. So this system is designed to avoid having that. We have a control system that can actually detect the onset of that type of reaction and back off so that you don't actually damage the core. That's a blank.
Yeah, the bottom has some kind of.
We're testing different salts and seeing how they affect the base metal.
Okay.
And so we've tested different kinds of metals. And
hasn't that kind of thing been done elsewhere and years ago kind of thing?
Yeah, and that's why we selected, and so these actually work really well. This material. We still wanted just to try it on the pieces that we got to see how the chemicals that we put in there.
I'm just curious, the numbering system you have here, what's that about?
So that is actually about the uniformity of the wall thickness. This is actually Schedule 160 pipe, and so we actually took, so that's showing the variation in the thickness of the wall.
So this is not uniform around?
It's pretty close. It's about as close as you're going to get. It's kind of funny because the vendor that we we asked them specifically. We said, this is what we need. They said, okay, and they said, yeah, we've got these pieces that fit within your specifications, and they sent us 3 pieces of pipe. And of the 3 pieces that they sent us, only 1 was even close to the specs that we had agreed on before they shipped it to us. So this is almost $1,000. Each of these pieces is almost $1,000 worth of pipe.
Wow. What's the tolerance?
We asked them to have it within 20 thousandths on the wall thickness around. Well, when we got the 3 pieces of pipe, it was clear that only one of the pieces was even close enough to do something with. And we had loud discussion with them, and we ended up shipping them. These things are not, they're not light.
Got your finger
Yeah, you
pinched
don't
in
want to
there.
drop that on your toe.
Yeah, that's what. How many pounds? 70?
No, that's probably only about 30 pounds.
Okay.
But
Yeah, I
but
didn't lift it.
shipping that back and forth. So shipped it back to them, and they said, "Oh no, it's the exact pieces we sent." But the pieces that came back actually were within spec. So they shipped us some pieces that were not the pieces that they said they were going to ship us. So
Do they actually machine that into that shape? Or is it another process?
no, it actually comes out of they have a machine that actually extrudes the pipe.
Extrudes, okay.
But it's you can get some pieces have some dyes have much better tolerance than other dyes, and so they all the pipe will withstand whatever specs. Schedule 160. I don't remember exactly what the specifications are for Schedule 160.
Jumping forward to production, where you're making these things,
Right.
would that become a limiting factor? Being able to get that kind of tolerances that you need?
No,
Okay.
I don't believe so. For this, it's much more of an issue for
One off.
yeah. Well, it's we're trying to if we can raise enough money, our intent is to take over the space next door. The company that was over there is vacated now, but we don't have enough money to take over. We'd like to set up 5, 7 of each type of reactor. We've got both wet and hot, wet boiler and the HHT boiler system. And so we'd really like to set up multiple systems, because it's something that we expect to be able to replicate, so that when we do have it ready, we can actually just create a system up, ship it to an OEM, send one of our engineers with them, help them set it up, train them on how the system actually operates, that you can turn it on, tune it. We'll work with them on how to do the tuning, and then we'll work with the OEMs to set up their own engineering of a product using this technology.
Would this be an appropriate time to ask the question, if not, we can postpone it, of why the tolerances and how that reacts to or how that affects the LENR process?
Well, actually, the mechanical tolerances that we're talking about on this aren't to do with the LENR process. This is development work. So the first one of these that we actually have machined and have put together and all assembled, we actually static pressure tested it to 6,000 psi. So something that's going to go in your house probably only has to be static tested to 3,000 psi, but because we're pushing the limits on everything.
So this is part of the boiler?
This is the wet system. So if you have, I think I was talking earlier about you start getting luminescence, you start getting light generated on the surface of the core. That's very destructive to the core. It eats the material. Basically what happens is your cooling system can't carry the energy away fast enough, and when the water flashes to steam, you get effectively cavitation damage. Anybody that's worked with pumps, you have a centrifugal pump, you have the same pipe diameter on the inlet and outlet, it'll just eat the rotor. It'll just literally eat the rotor. You get that kind of damage on your core, obviously it's not going to last. So that's why the wet system operates at pressure. We have, somebody was killed years ago at SRI. They were trying to do a pressurized system, but it wasn't like an SEM certified. We haven't taken these through the SEM process, but we do have had a certified pressure test operation, do a certified pressure test on it. We have a FIKE rupture disc system in there. Rupture disc is, very, very fast response time. So if there is you have excess HOH built up in the headspace and you get a catastrophic recombination, the thing's been pressure tested to 6,000 psi. The rupture disc is set to 2,000 psi. The rupture disc goes, there's no danger of anybody being hurt in our systems. We're doing real engineering here. This isn't, fly by night.
All right.
Risk people's life and limb.
Okay.
Mine especially. This piece here is actually allows us, this plexiglass vessel has actually been tested to 600 psi. And the neat thing about that is it allows us to go in and test it at very low pressures, atmospheric pressure up to a few psi. When we have a set of parameters that we see is working, we can pressurize it a little bit, see how changes in pressure affects the reactivity of the system. We can then remove the caps and put them into exactly as they are. Put them into the pressure vessel, high pressure vessel, and start. We have a starting point on where to put the signals through.
So it's kind of a jig. Would you?
So this is a jig. This the end cap fits in. The end cap drops into this holder. The cap fits in. The cap fits into these. Into this piece. There's additional caps that make the electrical seals, and then the whole thing slips into this. There's another piece just like that bolts on here, and we can adjust it and put it into our safety cube where we run it and run tests.
Okay.
And it's basically identical to the pressure vessel dimensionally, but you obviously don't build up pressure. You don't do recombination. You just flush the hydrogen and oxygen out of the system so that you don't wind up with an explosive potential.
Is this where we're headed next?
This is where we're headed next. This is the cube room.
You have like a plexiglass, like a cage around it. Is that plastic or glass?
That is actually Lexan.
It looks pretty good. What, quarter inch?
Half inch.
Half inch.
Yeah, it's half-inch thick Lexan.
Mm-hmm.
So you could shoot a 45 at that, and it will not go through.
Huh.
Yeah, this is the user interface. So there's a lot of tabs there that show all different aspects, and we're collecting data. We log data every 10 seconds.
So this is undergoing right now. This is.
We're doing sort of calibration testing of the system. You can see it's holding it to within pretty much within 0.8 plus minus 0.6 degrees, and that's the power. So the power is varying between 220 and 250 in spikes here and there. We're working on refining the control system so that's actually tighter.
Would this be an appropriate time to ask the question on this chart of kind of the input versus output and over unity kinds of things?
So what we're still in the process of tuning this. We have a little bit of a gas problem. So this is showing this is actually showing, this is the delta. This is showing that we're supposedly getting 80 watts. I guarantee you we're not getting any excess energy out of the system right now. It's a band heater heating it. And we know what's causing that problem. We haven't had a chance to fix it yet. Before we actually start running the issues and we finish getting all the materials aspects ironed out on the system, that'll be reading 0 when we're using the band heater and the internal cartridge heater. So the heat source is actually directly inside the vessel. That'll be showing 0 plus minus some number 0.
And then when you have this running optimally, as I imagine you have in the past, what would those charts look like?
the variation on the power, so the red is the power going in, and it's on this scale over here. That number is actually a lot tighter, and this number right now would be hovering right around 0, plus or minus 5, maybe plus or minus 10 watts.
Okay.
When we're running under the just characterization is what we're doing now.
As kind of an overview, should we run through this flow chart here really quick? Would that be a good place to do that, or?
Sure. So right now we've got a three-phase programmable AC power source. We use that to provide our Q pulse voltage and control the catalytic recombination system, and the band heater and/or cartridge heater inside will power either one. So that gives us power collection data from that source, and then we have an electrolytic supply, and that goes through the PC board that actually drives the cathode directly. These are both the Q driver PC board and the electrolytic driver PC board. That's actually one PC board that controls the whole ball of wax. And then we have different flows pulling heat out of the system, and we read the temperature of the water on the way in and the temperature of the water on the way out. We have flows going through all of them. I can show you the flow page here. So right now we only have one jacket, which is actually below where it should be right now, with water flowing through it, and that jacket is pulling. It's probably pulling a little less than 275. Like I said, we've got an air leak in the system right now that we will get ironed out. That's why it's showing more power coming out than is actually coming out. But everything everything runs through a real-time control system, compact real-time control system that does the data collection. I can actually turn this off, walk away, come back, turn it back on, and it'll continue to store data on the control system. This will come back up and just show you what the status of the system is.
What's the longest that you've run this continuously without stopping it at any given time?
This system here?
Yeah.
We ran electrolysis, I think for 3 days continuously, but there's still materials issues in that. So the cathode that we had in there is not actually an active cathode, but it does allow us to run electrolysis and profile how the recombination energy and the electrolysis energy and everything going into the reactor, what it looks like when there's not anything happening. So that's the kind of work that we've done on this system.
Do we get to go inside, or do we just from outside here?
Yeah, we can. You can go in if you want. There's.
I'd like to be able to just do a walk around of the.
Okay. Sure.
And we can come back later and take pictures, right?
Yeah.
Okay.
So that's the boiler. It obviously doesn't look like much other than a large insulated something. And so we have 4 different streams that we can pull energy off of the system with. The argon tank has multi-purpose. We've got a different kind of connector going on there that will go to the old power reactor system.
That's the argon tank there?
No, this is the argon tank there. That 300 cubic foot argon tank. And then those are platinum RTDs that you see coming out through the T. Then we have, this is the rupture disc. Comes out through here, goes through a big muffler into the bucket down there, just behind the yellow handle. This is the piece sitting on top of the nest lab. There is a bubble trap to trap air bubbles that are in the flow piece. If we go down just a little bit here, that's actually a nest lab, which is a temperature controlled bath. Right now it's set to 45 degrees. Just to kind of limit the amount of heat that the water pulls out of the system. And
And this is the wet reactor, correct?
Yes, this is the wet system. We have an argon tank there, so we can actually blow water out of, blow the moisture out of water jets that are being used, and that allows us to stabilize the system a lot more quickly. We're in the process of trying out different control algorithms on the system right now, but that's for the electric temperature stabilization system. So that's what allows us, will allow us to get cleaner information when we're actually running it. So this is the compact real-time control systems. Those are programmable power supplies, so we can supply up to each one of the smaller supplies can supply 50 amps of electrolysis current, and then we run that through the PC board.
Is this a genuine piece of cardboard?
That's actually just holding the insulation up against the bottom of the reactor. Is all that's doing.
Yeah, what, 20 wires, electrical wires between these two systems to do communication?
Yeah, at least. There's
What do we have up here?
well, that's yeah.
I should know what that is.
That's just a transformer.
Yeah.
So that's
What are the lights for?
So the lights are for, so like there's a pump that's supposed to be on there. Is it installed? We need to know whether the control system is. So come over here. So right now we've got a light plugged into the piece that's supposed to be running the water pump, and that's controlled from the front panel here. So I can tell them the pump is on, and we can plug different components in. The lights are in series. Sometimes some of the voltages that go out go between 0 and 240 volts. That's pair 120 volt light bulbs in series, and you can get a rough estimate on what the voltage is set to based on the brightness of the bulbs if they're plugged into something.
I'd like to talk to you more about that later because that sounds really clever. I've not heard of that before.
We've got these programmable AC sources, and so that's just a handy visual indicator to show the pump is just 120, plugs into the 120, and that gives us quick feedback on what's actually happening.
Just tell me if I'm filming something or going somewhere I shouldn't. I'm just gonna.
Well, you can't really see that much from back there, other than it's not a trivial system.
Yeah, sure.
I was just saying, beautifully constructed.
Well, we have the full engineering team here. I've got 3 mechanical engineers and Sal, Jim, Roger, Ron. Four electrical engineers, a couple of designers, a couple software engineers, all working. We work as a team, and it's almost pretty much all of the engineers can at least understand some aspect of at least one of the other disciplines that's involved in getting this reactor, getting the reactors together.
Is that intentional compartmentalization or just the complexity of the whole system?
If I could have 10 engineers that understood, at least could converse intelligently with all of the other engineers and all of the other disciplines,
mm-hmm.
things would move even faster than they are.
Mm-hmm.
So there's about 13 people in the group now. Many of them are not working full-time on the project because we don't really have money to really pay 13 full-time employees.
Mm-hmm.
But
you just barely got some money.
We do have money, but as you can tell by looking at this, the hardware is not cheap.
Mm-hmm.
So,
but you had this before, didn't you?
we had some of this. No, the power reactor did not run on a real-time compact Rio.
Okay, so this is new equipment here that you got with the recent money?
Some of this is new equipment. A lot of this is new equipment. What we had before was not in a rack, and this has actually been designed so that we can actually wheel this into a shipping container, into a shipping crate, and put it in a truck and send it somewhere.
For a second, do you want to pretend like you're talking to a layperson and just say, okay, here's what's going on in this reactor. This is where the
Sure. So
hydrogen goes in, etc.
So what's going on here? We have a constant temperature water bath. This is maybe a little bit above, the average version. So in order to figure out how much energy you have coming out of the system, we use the electronic meters, and we have some additional meters wired in that measure the amount of electrical energy going into the system. Mm-hmm. Then to measure the thermal energy coming out of the system, we have a temperature-controlled bath and precision flow meters that measure how much water and exactly what the temperature of the water is on the way in.
These are the flow meters here?
Well, no, these are actually temperature sensors. These are platinum RTD temperature sensors. The flow meters are actually in line. There's 4 different flows that we can control individually. And so that measures how much water is going in, what the temperature of the water is on the way in. These measure what the temperature of the water is on the way out. And based on that, you can calculate exactly how much energy is being removed from the system.
Roughly speaking, in kilowatts or fractions of a kilowatts, how much energy will this thing produce?
So this is not built to withstand the full capabilities that I believe the cores that we've designed to fit into the system can produce more energy than this configuration of the reactor will be able to remove. This configuration of the reactor should be able to remove about 800 watts of thermal energy production from this system. Mm-hmm. We can add another. We've actually already identified the components, the pump that will actually be able to circulate electrolyte through there, which will remove heat from the core much more quickly. And with that system, we'll be able to remove possibly as much as 30 kilowatts of thermal energy from the system.
Wow. That from 800 to 30?
800 watts to 30 kilowatts.
Yeah,
because the only stirring that's going on in this system right now is electrolysis. Mm-hmm. Bubbles, coming up and causing, enhanced convection for heat removal within the system. That's all that's going on. In the original high-pressure wet boiler, we had a mechanical stirrer that went down there and turned around and wore out parts and caused all kinds of problems, shooting things up. So this one there's no moving parts. The only thing close to a moving part is the pump in this nest lab. Mm-hmm. That's helping to move water through there. We can enhance the effectiveness of that pump. We have another pump that we can add into the system to enhance the water flow through the system. But due to just we've got one of our mechanical engineers is working on computational fluid dynamics of heat transport within the system, given the mechanical configuration of the system. So as is, by adding a pump that will actually take electrolyte out, hot electrolyte out, cool it down, run it through a pump. That whole loop is pressurized. That'll be able to withstand, 6,000 psi pulse. Even though the rupture disk is at 2,000 psi, 1,900 is the guaranteed hold limit. So that external heat exchanger pulling out hot liquid and pumping cooler liquid back into the system will really enhance the heat transport capability of the system. And so it's designed to deal with that. But that's a whole other level of complexity. Why go there until we get this portion ironed out?
Okay. This is silly, but can we go ahead and open the water bath?
Yeah, sure. And you can see there's some bubbles floating in there, and that's what's causing the thing to read excess energy, even though we know there's no excess energy. in there. So it's just distilled water in there.
Okay. Also, regarding this this shield that you have around it,
Yes.
what's the primary purpose of that? Safety in case
Safety.
something, you know?
So have you ever shot any of the lab down at SRI?
Not yet.
Okay, so Mike McCoubrey has a little more sturdily put together, a little more sturdy than this. They've got a lot more steel connecting the various panels of Lexan.
Mm-hmm.
And Fran's rated, this is ballistic grade. I don't know if this is actually ballistic grade Lexan, but it's pretty sturdy stuff.
Mm-hmm.
And so when I first started working with the pressurized reactor system, like I said, you know, the pressurized systems are vicious. They're really vicious. It's really dangerous. You got to put together a containment system like what we use here.
Mm-hmm.
And so it was actually killed down there from, like I said, from working in a pressurized reactor system that was not a properly engineered pressurized reactor vessel.
You say who was killed?
Back in the 90s, early 90s, I think. Somebody was there, one of the guest researchers was there, and they kind of fashioned together a pressure vessel, but it was not done by, you know, a full, you know, qualified mechanical engineer. And they went in and picked up an experiment because something didn't seem right, and when he picked it up, it flash recombined and it killed the guy.
Wow. Seems like your safety has a lot of redundancy, a lot of layers.
It does. So there's the white noise that you hear. There's that fan is pulling 1,500 cubic feet per minute of air through this system. So there's sodium hydroxide solution in there. If the rupture disk goes, a lot of it will condense out going through the muffler, but you do get a fair amount of steam. We actually have had rupture disks let go, say other software systems failed or whatever. The rupture disk went, and you get this big whoosh of steam that comes out of there. It goes,
Mm-hmm.
right? It's not an issue.
Mm-hmm.
It's not a problem. So,
Okay. Let's take some photos.
yeah.
Okay.
So this is the phase 2 reactor system that we got our first 2.1x result out of. It's been decommissioned because there were a lot of mechanical problems with this. So what we're using it for now is materials testing. So we took out a lot of stuff, so there's more room in there, and we can put in various types of materials that we're testing for possible use in the third generation reactor. And this is the mechanical stir rod. So this screws in and attaches to this electrical magnetic transfer mechanism and spun around. So this is a magnetic coupling mechanism that this thing can go into, and so this thing was in there and spinning around and causing all kinds of grief because the Teflon bushing here would wear out, and this would get off center, and it would scrape stuff off, and it was a nightmare.
Okay.
A lot of problems, and getting the electrical signals to pass through. There are just all kinds of problems. So now we're just using this for materials testing to make sure materials can hold up to elevated temperatures, elevated pressures. So this is the HHT system. There's a lot of software work going on right now.
I had thought that the HAT system was only up at
down at SRI.
SRI.
Nope.
Mhm.
We actually, because I live here in Berkeley.
Ground yourself or get shocked.
Yeah, so what that's about is, especially when when it's dry out, it's not that dry out, but when it is really dry out, you can draw an arc from that far away. So if you're holding on to this, then you don't feel the zap as much as if the arc leaves from your fingertip. So
Wow.
that's what that's about. And yeah, this is just all parts that go into the construction. of the system. So
Okay, an argon
all
tank?
another argon tank. We've got an inactive standby and an active tank, and so you got to. There's a lot of things that you have to control in order to have a viable, commercially viable reactor system. That MKS Cirrus 2 top of the cart there is a quadrupole mass spectrometer. Does masses 1 to 50.
You usually only see those in universities, they're so expensive.
Yeah, it's about $50,000 piece of equipment.
There's Mr.
But
B.
Gives us a tremendous amount of real-time analysis capability. And so yeah, it's probably better not to go behind this one.
Okay.
And allows us, yesterday, Fran called me up yesterday, at 6 o'clock, Fran called me up and said, I've got this problem, the hydrogen keeps turning off. So I went in and looked at the system and looked at what was going on and figured out what the problem was. And the problem was, and so the software for the control system actually talks to the mass spec. And we actually had, due to some gas flow issues, we had some oxygen incursion. Well, the software detected that there was oxygen leaking into the system and it shut off the hydrogen. So, figured out how to fix that problem, short term at least. And I'll actually be going down there this afternoon. The red box on the wall there is an explosive gas detector, and that's really helpful for finding hydrogen leaks in the system. I'll take that down there with me.
Handy to keep one of those around in this kind of environment.
Yeah.
Tell me if I'm filming anything I shouldn't.
Yeah, no, that's fine.
Okay.
I may edit out some of the angles of that top bit there, that PC board on the top.
Okay.
Delete those.
I haven't taken a close-up of that, so I think we're good. Now, do you want to give us the lay version explanation of where the reactor is, what's going on, where the hydrogen comes in, where the...
So that thing, this thing here is the reactor. This is where the reactor is. This is cooling water. We've got cooling water. This is for the gas flowing through the jacket. This is for the gas flowing through the core. It goes from a gas to liquid heat exchanger, and
I can take videos too. I can take videos too.
And so we've got all kinds of thermocouples measuring the temperature of the system in various places. We've got pressure gauges that measure the pressure of the gases at various locations in the system. And then we've got pumps that allow us to pump the gas through the system. We have this is basically just some comm information that's on here. I don't think we even have the control system right now. We're debugging another piece of equipment. So our scaled up pulse generator is not working yet, so we bought this other piece of equipment, and people can see it. Doesn't have enough oomph to do to really produce an effective Q pulse for a system this big, but it does have the edge speeds that allows us to diagnose mechanical problems with the system. So it's a signal source that we use for design problems. And that's
This is the reactor vessel back here.
This is down in here is actually where the hydrogen hot tube lives.
And remind us of how hot the hydrogen hot tube is able to get.
So the design goal, the design target for the hydrogen hot tube is kind of 500 on the low end,
Celsius.
800 Celsius on the high end.
Mm-hmm.
In that range. Target.
And where are you at right now?
Where we're at right now is solving mechanical design issues. Is where we're at right now.
So you don't have a temperature that you can mention that you've achieved?
No. Well, using an electric heater, we've had it up to 650 degrees C, but that's
Oh.
using an electric heater.
What about an SRI? Are we talking about SRI, or is this
So at SRI, we've had a few episodes of heat that I haven't been able to come up with an explanation for, other than LENR reaction actually generating the heat. You know, we brief period of excitement last night where we thought we were, you know, like, oh, the temperature's going up. What's going on? But then we looked. There was oxygen incursion in the system. It was clearly chemical energy that was being detected. So, you know, so there's a leak that's developed in the system at SRI right now that, you know, well, that's one of the reasons I'm taking that down there. So there's on the one hand, it's kind of like a nuclear fission reactor, San Inferno or whatever, where you get a bunch of uranium, you stick control rods in and out of it, and you've got an electric power plant, right? It's a little more complicated than that. So, you know, in theory...
They don't call them nuclear scientists for nothing, right?
Right, yeah. So, you know, in theory, I consider it, you know, it's pretty straightforward what's going on. In actually designing a system that's commercially useful, it's very involved. There's a lot of pieces, and you know, one of the what's unique about this group is that we have a very multidisciplined team, and so I don't have the expertise for all of the areas, but I can at least understand what people in all the various areas are talking about, and even our CEO, Robert George, we were back. He's a mechanical engineer, and we were back, and he said, "Well, why don't you use a transistor instead of a FET for that?" We're like, "Oh, we didn't even think about that." So, again, it's a multidisciplined team. That's really what it takes to bring something like this to market.
Now, given the complexity of this, you know, it's not something obvious that a garage mechanic could pull together and see the pieces in a schematic and put it together and have it work. There's a lot of that goes into it.
Even, and you know, I think the NSA is a disaster for this country because every commercial company's data is being pooled by one central agency. That's just a disaster. That's a
intellectual property.
Intellectual property. It's a dream come true for industrial espionage people. It's a nightmare for every company in this country to have their data being aggregated by one central location. It's a terrible idea. The kind of interesting thing about this is
we have an example of Snowden, who was a whistleblower for good.
Right.
Think of all the people who were in there saying, "Hey, I know somebody who would like this information," and under the table, there it goes.
Exactly. And so they reduced the number of system administrators. Oh, that's just wonderful. Thanks, but no thanks. The interesting thing about this is, without a very multidisciplined team, they can download all of our data off of the computers. They're not really a whole... Sure, it gives them a big leg up, but they're still not going to be able to assemble a working system. They have all of the disparate pieces, but they still don't have the know-how on how to assemble that data. So, do I worry about that? I've got enough things to lose sleep over. I don't worry about that, but it's annoying, you know. Our government has no business doing what they're doing.
And you got to get it off your chest once again, so you feel good, right?
Well, I'm just saying, you know, there's the companies, cloud companies have already lost business because of what's going on.
Now, in terms of what most people are going to want to see some over Unity. At what point are we going to be able to see that today?
You're not going to see that today.
Okay.
You're not going to see that today. We are making tremendous strides in moving these systems forward mechanically.
But you have achieved it.
Yes, we have.
Right.
We have achieved it. We have really excellent data from the phase 2 reactor. I have a lot of data that's available, and that data is available on the website for both phase 1 and phase 2, showing that it is repeatable.
I clicked a bit around on your site just today, and how would somebody get to that information?
So, and show you right here.
Brillouins energy.com.
So brings up brillouinenergy.com. You can go to our technology. So overview. You can actually. This is a scrollable page, and if you go down to the bottom of that overview page, there's a bunch of links on that page. At the bottom of that page, here's the technical PowerPoint. That's what Tom Claytor watched several times to figure out how to do his independent test of the hypothesis that he's done.
He replicated the system, right?
Well, he actually didn't do a replication. What he did was he said, okay, based on first principles, if I assemble a bunch of stuff like this, I should be able to generate nuclear reactions. He did that. Last time I talked to him, I said, I've been trying to get a report out of him, and he said, well, I'm, better than 80% certain that what you said is really the way to do it. He's actually working with Roger Stringham out of Hawaii right now.
The sonofusion guy.
Huh?
Sonofusion.
Yeah, Roger Stringham's doing sonofusion, not to be confused with some other people who claim sonofusion. So, he's been disinvited for running experiments at Los Alamos. Tom Claytor is retired, but he still has access, so he can take gas or liquid or whatever into Los Alamos and have them run diagnostics for him on the materials after the fact.
Would that to be able to measure maybe some electromagnet or some nuclear species that might show up?
So yeah. So he's run more than at least 8 tests to do his first principle tests of my hypothesis, and all 8 times it generated tritium. All 8 times it generated tritium. Now, I've talked with him about what he's doing and why he's getting tritium as opposed to heat and helium. It's not a huge amount of tritium, but also they're really set up to detect tritium much more so than helium. Supposedly they're working on improving their helium detection capability, but Los Alamos is sort of world-renowned for their expertise in tritium. So, he ran, several of his experiments were run with isotopically cured deuterium, and it generated tritium. There's no way around it, that's a nuclear reaction.
Right.
I think, people who have looked at your site about LENR probably aware that the guys at SPA Wars, San Diego Space and Naval Warfare Systems, were shut down. Their investigation of LENR was shut down because a report got out and it embarrassed some general who got called on the carpet for allowing any money at all to be spent on LENR research. They're doing a lot of really good work there, and politically it's very unpopular though, and they were shut down. So Tom's been disallowed to run his experiments at Los Alamos. So he's doing experiments. He's got us set up in his house, his garage. That's Roger Herrera, one of our electrical engineers. Does a lot of tech work for us. And so we've been having some communications issues with stuff, and so he's solving some problems there.
And making some.
Yeah, solving some, making some new ones. So anyhow, so
The
that's
idea is to solve more than you make, right?
exactly. Try to take at least 2 steps forward for every step you take back.
Okay.
So that's that's just sort of what this field has been dealing with. I would like to say confident, but I'm not. But I'm hopeful to actually get Tom to write up a report of the work that he's done testing the Brillouin hypothesis that really seems to work. There's people who put pulse power through hydrogen-loaded transition metals, palladium, titanium, tungsten, nickel. Very reliably, you can generate nuclear reactions. So what we're working on here is focusing on creating an industrially useful system to do that on a repeatable, reliable basis. And there's just a lot of engineering that goes into that. It's a lot of hardware, and that's what we're raising money for.
Could you mention briefly what some of your milestones or goals are, so that you get to the point where you say this is replicatable? We've got a level of stability here.
Right. So the milestones was initially getting a basic design done, and now we have at least 4 different cores that are in various stages of design and processing, setting up all the various machining steps that it takes to assemble things. Once you get to 500-600 degrees C, 700-800 degrees C, the number of materials that you can work with really drops drastically, and you have to figure out where you can contain the heat, where you can transport the heat, where you can use what materials, and how they're going to hold up in the various circumstances, and that's what this design effort is about, is solving all those mechanical issues. So based on the progress that we've made so far, I'm pretty confident that by the end of 2014, I said last year I thought by the end of 2013, but we didn't raise as much money as we hoped. And, we've got a raise going now, and, if we can get several more $1 million in here, we can open up the space next door and get a bunch of these reactors going, so we can test multiple cores at the same time in parallel. Build, you're looking at about, minus the oscilloscope, just the rack and everything, you're looking at $160,000 worth of hardware.
Finish your sentence about by the end of 2014.
So based on the progress that we've made so far, I have pretty high confidence that by the end of, we keep getting money in, by the end of 2014, we'll be at a position where we can have SRI will actually be able to start writing a report. That report probably won't be public, but it is a report that we'll share with OEMs who are interested in actually using the technology to produce products.
So 2014 could be the beginning point of the OEMs starting their engineering?
Yes.
Mm-hmm.
Yes.
And they would engineer to their applications.
Right.
Mm-hmm.
Right.
Would any of them, with their application, because it's the same scale that you're using here, be able to go immediately into production, so to speak? Or they're going to have to go through some testing and...
Well, a lot of what you see here is for calorimetry.
Mm-hmm.
So the OEM systems will, in some respects, will be simpler than what we're doing here.
Right.
But the immediacy of it is, kind of depends. These are, the OEMs have to warranty the systems that they put out. Depending on the scale, if they're going to produce 10,000 a year of something, you can handle 85-90% pass rate at your assembly point. If you're going to produce 50 to 80,000 of something, you need really at least 90%, 95% pass rate.
What are you calling pass rate?
Pass rate means you take one of these pieces, 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 you put them all together into a finished product, and that finished product passes spec tests and can be put in a box and shipped to a customer.
Okay.
That's pass. So
what was typical for the layperson in the industry for a pass rate?
So that's what I'm talking about. You're producing maybe 10,000 of something, 85.
Well, I'm talking about kind of, similar industry. What would their pass rate be? It's something that's already in the marketplace.
Something that's already, well, it kind of goes by how many per year. If you're in the auto industry and you're producing millions of something, you've got a 5 nines pass rate. And if you don't, some vendors getting their butt kicked.
Yeah.
Because you can't have product dropping out. Well, the further something gets down the line towards completion and being shipped, before you catch a problem, each stage down the line you get, it gets 10 times an order of magnitude more expensive to fix it.
Right.
So when they get like the cars, when they get the recalls, it's like they can kill them. Just
it's really bad for a car company to have a recall on something, and they may only recall 50,000. They're producing 100,000 cars of a particular car a year. They say, oh well, we're recalling 370 of these. That's because they have very good tracking of their supply chain, and they go, they start seeing failures after it's shipped. They go, oh, it's cars that had this part from this batch from this manufacturer, and that manufacturer either just got the boot or their ass kicked, and they clean up their act or they're gone.
Should we take some pictures in here?
You have been.
Hi, Sterling Allen here. I just got back from my trip to see Brillouin over in near Oakland, California, and I'm going to be showing 3 videos from that trip with Brillouin, and this is the first of 3. The first one is we're going to show their Berkeley facility, which is where their headquarters are, and they've got their wet system and the HAT system there. We saw both of those running and in process of taking measurements and whatnot. And then the second video, we're going to show SRI International, their HHT system, which is the hot system, which gets up to 600 degrees Celsius. They have an HHT system there. It's a little more, there's more sophisticated equipment measuring that, but it's pretty much the same setup, but a little different in terms of the equipment that's measuring it and where the wires are running and whatnot. And then the third video will be kind of a roundtable discussion where we're talking at SRI with Mike McCubry and some others there. Actually, there's 4 videos. I've already posted the first video, which was an interview I did with Mike McCubry after everything was done. So,
Mike McCubry and Fran Donzella and my team here had a conversation actually about that exact thing. There's a video on our website showing showing some fire coming out of the core, and we think that the light that comes off of that out of that you see in that video is actually metal ions being blown off the surface of the core. As soon as you get luminescence coming off of the core, sustained luminescence like what you see in the video, phase 1 video on our website, it damages the core and it eats it very quickly. So this system is designed to avoid having that. We have a control system that can actually detect the onset of that type of reaction and back off so that you don't actually damage the core. That's a blank.
Yeah, the bottom has some kind of.
We're testing different salts and seeing how they affect the base metal.
Okay.
And so we've tested different kinds of metals. And
hasn't that kind of thing been done elsewhere, and years ago, kind of thing?
Yeah, and that's why we selected. And so these actually work really well. This metal, this material. We still wanted just to try it on the.
This is really the second video, second of 4, and by the time we're done, there might be 5, but we'll call this video 2 of 4 for now, and we're going to show you the facilities there in Berkeley.
This is sort of stages going through the new wet boiler system. This is the pressure vessel blank. Then there's a lot of machining that gets done on that, and then we've got these caps that slip into the end. We have a plexiglass version, so this fits up in here, and we have a piece that goes around it. There's caps top and bottom, so this allows us to assemble a complete system and operate it, and we'll be able to see visually when the system goes active. When you actually have a reaction happening, you wind up with a cloud forming around the cathode. When it's just electrolysis going on, you have bubbles nucleate and they float up. When you actually have a reaction going, you get a cloud emanating from the cathode in all directions.
So it actually luminesces.
No, if you actually get luminescence out of it, it's damaging the core.
Okay.
Kubri and pieces that we got to see how the chemicals that we put in there.
I'm just curious, the numbering system you have here, what's that about?
So that is actually about the uniformity of the wall thickness. This is actually Schedule 160 pipe, and so we actually took. So that's showing the variation in the thickness of the wall.
So this is not uniform around?
It's pretty close. It's about as close as you're going to get. It's kind of funny because the vendor that we asked them specifically, we said this is what we need. They said okay, and they said yeah, we've got these pieces that fit within your specifications, and they sent us 3 pieces of pipe. And of the 3 pieces that they sent us, only 1 was even close to the specs that we had agreed on before they shipped it to us. So this is almost $1,000. Each of these pieces is almost $1,000 worth of pipe.
Wow. What's the tolerance?
We asked them to have it within 20 thousandths on the wall thickness around. Well, when we got the 3 pieces of pipe, it was clear that only one of the pieces was even close enough to do something with. And we had loud discussion with them, and we ended up shipping them. These things are not, you know, they're not light. You
Got your finger
yeah,
pinched
you don't
in
want to
there.
drop that on your toe.
Yeah, that's what. How many pounds? 70?
No, that's probably only about 30 pounds.
Okay.
But
Yeah, I
but
didn't
you know,
lift it.
shipping that back and forth. So shipped it back to them, and they said, "Oh no, it's the exact pieces we sent." But the pieces that came back actually were within spec. So they shipped us some pieces that were not the pieces that they said they were going to ship us. So
Do they actually machine that into that shape? Or is it another process?
no, it actually comes out of a. They have a machine that actually extrudes the pipe.
Extrudes, okay.
But it's you know, you can get some pieces have some dyes have much better tolerance than other dyes, and so they all, you know, the pipe will withstand whatever specs. Schedule 160. I don't remember exactly what the specifications are for Schedule 160.
Jumping forward to production where you're making these things,
Right.
would that become a limiting factor, being able to get that kind of tolerances that you need?
No, I don't believe so. For this, it's much more of an issue for
One off?
yeah. Well, it's, you know, we're trying to we're if we can raise enough money, our intent is to take over the space next door. The company that was over there is vacated now, but we don't have enough money to take over. We'd like to set up, you know, 5, 7 of each type of reactor. We've got both wet and hot, wet boiler and the HHT boiler system, and